So, this is chapter 28 about interference and diffraction. So, looking at interference and diffraction. So, we'll talk about superposition and interference. We'll discuss Young's two-slit experiment. We'll look at interference in reflected waves. Then we'll talk about diffraction, resolution, and diffraction gratings. So, when two waves occupy the same space, their amplitudes add at every point. They can either interfere either constructively or destructively. So if you have two waves that are half a wavelength apart meeting, so this is the difference in distance two waves from the same source travel. That's d sine theta, and that equals some number minus a half, some whole number minus a half times the wavelength. If they are half a wavelength off, the two waves will be 90 degrees out of phase. When one is going up, the other is going down, and they will cancel each other out in a form of destructive interference. So that's destructive interference. Constructive interference would be when the two waves are aligned with each other and they add up. So interference is really only noticeable when the light sources are monochromatic. So all the light has the same wavelength, and coherent, where the two sources that are interacting maintain the same phase relationship over space and time. When this is true, interference will be constructive where the two waves are in phase and destructive where they're out of phase. So what happens is that you can ensure this occurs with waves by, usually this happens when the coherence happens because they usually come from the same source. And then they're monochromatic. So here, for example, if you have two radio antennas, and you add up the signals from two different paths, they will add up constructively when the paths that are sending out two radio antennas sending out the same signal. They'll add up constructively when the paths differ by an integral number of wavelengths, and destructively where they differ by a half odd integral number of wavelengths. So if they differ by like 1, 2, 3 wavelengths, they'll add up constructively. 1.5, 2.5, 3.5, destructive. So if you look at the two path lengths, that identical signals, the signals of the same wavelength in the same phase, travel, they'll interfere constructively if they add up to an integral number of wavelengths, and it's destructive if it's a half in between. So one of the classic demonstrations of this was Young's two-slit experiment. Where by running light through a single narrow slit, he rendered it coherent, and then ran it through two slits. So the difference in wavelength and then you can calculate the difference in wavelength, and you see this pattern of light and dark bands. So if light consisted of particles, the final screen would show two thin strips, one corresponding to each slit. However, if light is a wave, each slit serves as a new source of wavelets, like shown here. And the final screen will show the effects of interference. This is called Huygens principle. And if you do this with light, you'll get an interference pattern like this. with bright strip in the middle, then dim, then bright, then dim, then bright, then dim. And as the pattern on the screen shows, the light on the screen is alternating light and dark fringes corresponding to constructive and destructive interferences. And if we put together the structure, you could figure out the difference in distance between the light from each slit equals, the difference in distance traveled by one slit compared to the other is the distance from between the slits times the sine of the angle that it is at. And this is assuming that the screen is far away, but it boils down to distance between the slits times the sine of the angle. So the condition for bright stages is d sine theta equals a whole number, an integer times the wavelength. And then in between there's dark points. So what's going on is that effectively the light goes out a long distance to the screen. So the two paths are identical from this point where you draw a line perpendicular. And the difference is just this length here, which is the distance between the slits times the sine of the angle. And a little bit of geometry tells you that that's d sine theta. That this angle is the same as the angle as the light is traveling outwards. And so the fringes are numbered from the central being 0, the first one at each side being +1 and -1, and so on. Now, a very common form of interference that you'll see is interference with reflected waves. Where when you go from a higher index of refraction to a lower index of refraction, the reflected wave does not have a phase change. But when you go from a lower index of refraction to a higher index of refraction, there is a half wavelength phase change, so there will be interference there. But you can also get interference from reflection on the top from two different layers. So there's no phase change when light reflects from a region with a lower index of refraction. There's a half wavelength phase change when light reflects from a region with a higher index of reflection or from a solid surface. There's also no phase change in the refracted wave. And if you have light coming in at an angle and reflecting out, something like this can lead to, there's no phase change here, there's a half wavelength here, and then they can come out, and you can get this setup will give you constructive interference at 1/2 plus 2d over pi equals a whole number, and destructive interference at 1/2 plus 2d over wavelength, equals a half of a whole number plus a half. Because there's an extra 1/2 here at the reflection. And if you want to see something like this, maybe without this gap going on, if you've ever seen those colors on like an oil slick, that's caused by interference in the reflected waves or on a bubble. So this can also occur when light reflects and reflects from both surfaces of a thin film. This accounts for the colors we see in oil slicks and soap bubbles. So here there is a phase change for ray 1 of half and no phase change for ray 2 on the bottom. you not only path differences in phase changes and reflection, you also have to account for the change in wavelength as the light travels through the film. Um, the wavelength of light in the medium of index of refraction n. That n is theta vacuum over n. And therefore, the condition for destructive interference is where T is the thickness of the film is 2n T over the wavelength in the vacuum. So there's a factor of the index of refraction added in equals a whole number. And the condition for constructive interference is 2nt over the wavelength in the vacuum minus 1/2 m. And the rainbow of colors we see is because different angles end up corresponding to different distances in the film or different thicknesses of the film, different colors. And so you do see different colors for different thicknesses of film. And it also depends on the index of refraction. So it depends on the index of refraction of the film and the surrounding media. Where if you have like oil on water, oil has a higher index of refraction than water. There's a phase change at the surface and no phase change on the bottom. And then there's an effect from the distance traveled inside. It has to do with the angle. And DVDs depend on interference for their functioning. The signal's encoded as tiny bumps on the surface. And the reflected laser beam will vary in intensity depending on whether it's reflecting from a bump or not because of interference. So when you go through a change, there's interference, which causes darkness, which can be recorded. And a lot of these effects are related to the concept of diffraction, where if you have a wave that passes through a small opening, it will diffract and spread out. And that means after the opening, there are waves traveling in directions other than the direction of the original wave. It bends around the opening. And diffraction is stronger the smaller the opening is compared to the wavelength. Diffraction is why we can hear sound around corners, even though we're not in a straight line from the source. Sound waves are long enough wavelength that they diffract around doors, corners, other barriers. The amount of diffraction depends on the wavelength, which is why we can hear around corners but not see around them. And when light diffracts through a very narrow slit, we see an interference pattern from the diffraction from either side. We see what's called a single slit diffraction pattern. It's brightest in the center, and then there's a dim, and then a bright, and then a dim, and then a bright. And this pattern is due to the difference in path length from different parts of the opening. And the first dark fringe occurs when the width of the opening times the sine of the angle equals the wavelength. And the second is when the width of the opening times the sine of the angle equals twice the wavelength. And so on. The pattern is due to the difference in path length from different parts of the opening. And in general, the pattern we have is that width of the opening times sine of theta equals a whole number times the wavelength. And the positive and negative numbers account for the symmetry around the center. And you can see them if you hold your finger and thumb very close together. And here is a video demonstrating diffraction interference.
This is a laser, and I can use it to demonstrate something that you've learned from a very young age, which is that light travels through space in straight lines. The laser is shining onto the screen. You can see the spot where it meets the screen. And I can make the laser beam visible by spraying some water mist into its path. You can see the beautifully straight path that it takes. Now, you've probably also heard that light travels through space as a wave. And I can use this laser to demonstrate why scientists believe that to be the case. Now, to do that, I need a wire. It's a thin wire. It's only 100 micrometers in diameter. The wire is held vertically between these two clamps. Now, I'm going to slide this wire into the path of the laser beam. Before I do that, I'd like you to predict what you expect to happen to this dot on the screen. Most people expect to see a shadow where the wire blocks some of the laser light. So if this represents the circle on the screen, then most people expect the wire to come in front of the spot and leave a shadow. Let's see what actually happens. You can see here where the light has hit the wire, and on the screen you can see, well, it's not a shadow. There's no line down the middle at all. In fact, that's the brightest part of the pattern. And coming out on either side, horizontally, we can see a pattern of bright and dark regions. So what's going on here? We can only explain this pattern if we understand that light travels through space as a wave. The light waves travel from the laser to the wire, and they're diffracted as they pass either side of the wire. That is, they're bent into the region behind the wire. Light waves which have travelled one way around the wire meet up with light waves which have travelled the other way around the wire, and they interfere with each other in the region between the wire and the screen. So let's take a look at this pattern in detail. In the centre, we can see there's a bright spot. There is no dark line. What's happening here is that light waves which have travelled around each side of the wire are arriving in step, that is, in phase. The wave crests add to each other, leading to constructive interference and a bright spot. If we move a little bit further out on the pattern, we reach a dark region. What's happening here is that the light waves which have come round one side of the wire are arriving exactly out of step, that is, out of phase, with the light waves which have travelled around the other side of the wire. That leads to destructive interference. If we move a little bit further out, again we get constructive interference between the light waves which have travelled each way. Line down the middle at all. In fact, that's the brightest part of and the screen, which have laser to the wire, and they're diffracted as they pass. We can see a pattern of bright and dark regions. So what's going on here? We can only explain this pattern if we understand that light travels through space as a wave. The light waves travel from the laser to the wire, and they're diffracted as they pass either side of the wire. That is, they're bent into the region behind the wire. Light waves which have travelled one way around the wire meet up with light waves which have travelled the other way around the wire, and they interfere with each other in the region between the wire and the screen. So let's take a look at this pattern in detail. In the centre, we can see there's a bright spot. There is no dark line. What's happening here is that light waves which have travelled around each side of the wire are arriving in step, that is, in phase. The wave crests add to each other, leading to constructive interference and a bright spot. If we move a little bit further out on the pattern, we reach a dark region. What's happening here is that the light waves which have come round one side of the wire are arriving exactly out of step, that is out of phase with the light waves which have travelled around the other side of the wire. That leads to destructive interference. If we move a little bit further out, again we get constructive interference between the light waves which have travelled each way around the wire. And this pattern repeats as we go further out. Now, this is quite a simple demonstration to do, but the detailed explanation is really rather complicated. The key point to remember is that it's impossible to explain this kind of pattern without the idea that light travels through space as a wave.
So if you have something that diffracts through a small circular aperture, you get a circular pattern of fringes, and this limits our ability to distinguish one object from another when they're very close to each other. And the location of the first dark fringe determines the size of the central spot. So the sign of the angle that you can determine ends up being 1.22 times the wavelength. You know, the minimum size that you can, this is the location of the first dark fringe. So the size of the central spot is 1.22 times the wavelength over the diameter of the hole. So the smaller the hole is, sign of the angle is. So this, and Rayleigh's criterion relates the size of the central spot to the limit at which two objects can be distinguished. So if the first dark fringe of one circular diffraction pattern passes through the center of a second diffraction pattern, the two sources responsible for the patterns will appear to be a single source. So the size of the spot increases with wavelength and decreases with the size of the aperture. So on the left, well, on top here, this appears to be a single source, and below you can see the two sources can be clearly resolved. And so this is sort of a limit. There's sort of a resolution limit determined by the size of the aperture that you're looking through, that you're collecting, that you're looking through, and the wavelength of light. So you get better resolution the shorter the wavelength and or the larger your collection area. And a diffraction grating is a system with a large number of slits. And as you get more and more slits, the peaks become narrower and more intense. Here's the pattern for 5 slits. A normal diffraction grating has, I think the stuff we have has like 1,000 per millimeter, like 1,000 per millimeter is pretty common. Lots of slits. And the positions of the peaks end up different for different wavelengths of light. And so diffraction ratings will split light out based on their wavelength. And so they can be used to separate light out into a spectrum. So the condition for constructive interference in a diffraction grating is d sine theta, where d is the distance between the slits, sine theta times m wavelength. And there's many ways to construct diffraction gratings. So this is an acoustic optic modulator that diffracts light from acoustic wavefronts in the crystal, and tuning the sound off eliminates the signal, and changing the frequency modifies it. More common is a surface or that's got a bunch of lines etched on it, or a thin film with a bunch of lines etched on it. And you'll see, well, let me see if you can see the sort of the fact that there you can see that the diffraction grating breaks the light source up and shows you the spectra around it. I can show you guys in more detail than you're actually here. And one of the things that you can do with this is use studying the diffraction patterns created by like a crystal with X-rays lets you determine the crystal structure. So X-ray diffraction is used to determine crystal structure. The spacing between the crystal planes is close enough to the wavelength of the X-rays to allow diffraction patterns to see. And a grating spectroscope allows precise determination of wavelength. That's what most gratings are what most of the various spectroscopes and spectroscopy instruments in the big lab use. And this can be observed on various surfaces. Like if you look at a CD or DVD, the rainbow colors have to do with acting as a diffraction grating. But also if you've ever seen any of those like holographic that are all rainbowy colored printed things like stickers or cards or things, that is by taking the surface and embossing a pattern on it, you get that effect. So that's the end of chapter 28. So when two waves are superimposed, the result may be either constructive or destructive interference. Monochromatic light consists of a single frequency. Coherent light maintains a constant phase relationship. Young's two-slit experiment shows light and dark interference fringes. Bright fringes are d sine theta equals m lambda, where lambda is wavelength. Dark fringes are half a wavelength off. Thin films can form colors in reflected light through destructive interference of other colors. When a wave encounters an obstacle or opening, it changes direction. This is called diffraction. When monochromatic light passes through a narrow slit, the pattern of bright and dark fringes is produced. Dark fringes occur where W from sine theta equals m over wavelength, where W is the width of the slit. And resolution is the ability to distinguish closely based objects. Diffraction limits resolution. If two objects are separated by less than the minimum angle, they can't be distinguished. The minimum angle is 1.22 times the wavelength you're looking at divided by the aperture that you're looking through. And a diffraction grating is a large number of small slips, and the principal maxima occur at d sine theta, where d is the spacing between the slits, equals m lambda. So that'll be all for today. I think since we're well ahead of schedule and we might as well get ahead, I think I might just do the review on Wednesday. If that's okay with you guys. And then I don't know what I'll do next week, Monday. The plan was to do a review on Monday next week. But we're ahead of schedule, so I don't know what I'm gonna do on Wednesday. Well, I'll talk with you guys about it on Wednesday. How's that for a plan? So we'll either do another chapter, I'll pull something up, or we'll do the review on Wednesday and maybe I'll pull up, and we can just sort of mess around or something. We'll figure it out. Have a nice day.